All right, this is, believe it or not, the last lecture of the semester. So chapter 8, we learned about Lewis structures and then the VSEPR model, or the valence shell electron pair repulsion model, which allowed us to better visualize or predict the molecular geometry of a molecule. All very cool stuff. Chapter 9, you're gonna see we just kind of skim the surface of. It's just an additional consideration or just one step a little further in developing our understanding of that VSEPR model and how orbitals actually form between two elements that are bonded together in a molecule. So this will be a pretty quick lecture. And the recitation packet for chapter 9 is actually identical to chapter 8's recitation packet. You're just going through and adding this additional layer. So I'll revisit that at the end of the lecture. So without further ado, chapter 9, what is going on? Okay, so let's just really quickly review, and we're gonna actually, I'm gonna slide over to my other program. Yeah. We are going to review using a species that we've already talked about. So methane, right? CH4. You want to make sure that you have your periodic table next to you. Oh my goodness, I am modeling such bad behavior. Oh, nope. Here we go. Perfect. Sorry, plant. So make sure that you have your periodic table next to you so that you can really easily determine how many valence electrons each element has. So carbon obviously has 4. Our hydrogen has 1. We have 4 of them. So that means we have a total of 8 valence electrons. Okay, so let's just go ahead and make this Lewis structure, and then we'll see where chapter 9 comes into play. So we know carbon is going to be our central atom. And as we draw this, we can actually start thinking about that valence shell electron pair repulsion model and kind of draw it in a way that best reflects the 3D orientation of our molecule. This is much more accurate than if you were to draw it like that. It actually doesn't maximize the space between species, even though it looks on two-dimensional space as though it would. Okay, so here we have our methane, and I've used 2, 4, 6, 8 of my electrons all to create those single bonds, and I can see that I've used all my valence electrons. My duet rule and my octet rule are good to go, and so I have a accurate Lewis structure. Awesome. Okay, so let's unpack these bonds a little bit, right? All 4 of them are going to be identical. So we know if we were to draw the orbital diagram for hydrogen, it just has its 1s orbital and it has 1 electron. If we were to draw the electron diagram, just looking at the valence shell of carbon, right? So our valence shell is that 2s and 2p. So we have our 2s and our 2p. We know that carbon has 4 valence electrons. So if we were to obey our principles, it would look like this. So carbon has space for 4 more electrons, right? So let's just go ahead and draw those in, because we know that bonding is going to give us noble gas configuration, and these red electrons you can think of as being the contribution from each one of these hydrogens. So there's already something kind of curious about the way that I've drawn this for our carbon, right? So what's curious about it is right now it looks as though there are, 2 hydrogen electrons that are occupying the 2pz orbital. That seems weird. You'd think that you would need a carbon electron in order to have a bond, right? Because carbon and hydrogen are sharing. Also, if I were to draw this in a way that reflected the energy level, this would actually be Our carbon 2p would be a little bit higher, a higher potential energy. So you'd think that these electrons would have higher energy, and so there would be some kind of disparity between these bonds and the energy level, which would also correlate to their length, right? So keep that in your back pocket, and let's go back to our lecture slides. And what we're gonna see is that in order for methane to exist, the native orbitals, so these are the orbitals that belong to carbon. So we have that 2s and the 3 2p orbitals. Those native orbitals are going to hybridize, right? So if you think about a hybrid vehicle, let's say it's a Prius, you have a gas engine and then you have an electric car, and a hybrid is the combination of those two things. The same kind of hybridization, sure, is happening here, where we have our 2s and our 2p orbitals hybridizing, so that what once was one orbital at a lower energy level and 3 orbitals at a higher energy level is going to hybridize, so that we have 4 orbitals that are all the same energy, which is also, they're going to be the same energy, which is also called being degenerate. So to be degenerate means to be the same energy level. Okay, so let's go back to our other program. So what we see here is that we are not looking at this disparity, and instead, let me draw our hybridized orbitals in, oh, let's go purple, sure. Instead, what we see is all 4 of these orbitals are going to hybridize and create 4 degenerate orbitals that are intermediate between our s and our p orbital in potential energy, right? So this is increasing in potential energy. The carbon, right, we said carbon was green electrons. Let's stay to that. So carbon's electrons file in here, and then we have each one of our hydrogens with its 1s orbital filing in its electrons. And so by combining this single 2s orbital and 3 2p orbitals, we get our hybridized orbital, which is called a, this would, oh, let me just get rid of that, which would be called a sp3 orbital. So this is a hybridized orbital. Okay, so what is significant about this is that when we look at each one of these bonds in methane, they are equidistant, so they're all the same length, they have the same chemical properties. So we know that this is not the best model. Instead, this hybridization, the combining of native orbitals to create what are called our hybridized bonding orbitals, is a better representation of what is actually happening in our molecule. So everything we did here is old hat. Everything here is old hat. This is new. sp3 hybridized orbital. Very cool. So again, you can think of that. We call it an sp3 because you have one s and then you have your p, p, p. So 1s, 3p, and we write that sp3. Okay, so how do we figure out what our hybridization is? Well, we just went through this process, right? So we had CH4, we'd draw the Lewis structure, we'd think about the Vesper arrangement, make some adjustments to try to make it more accurately reflect the way the molecule's geometry is going to be, and then we can go through and say, okay, this is an sp3 hybridized orbital. So notice that our carbon in the methane molecule was sp3 hybridized. Our nitrogen here is also sp3 hybridized. What similarities do they have? Well, they all have tetrahedral electron geometry. So when we're looking at hybridization, we don't care if it is a single bond or a lone pair. The number of things, if you will, effective electron pairs around the atom that we're interested in the molecule is going to determine its hybridization. So here our nitrogen has 1, 2, 3, 4 things around it. It is sp3 hybridized. So these lone pairs are also existing in a hybridized orbital, sp3. Okay, here's another kind of a visual representation of this. So you have your s orbitals, your 3p orbitals. They hybridize and form these little mushroom orbitals, where this is a really small lobe, and this one's much larger, where your electron domain is largely existing. You still have that node of very low electron probability, and this would be in that tetrahedral arrangement. So one really cool way to draw these is what I call our orbital cartoons. So you can think of sp3 orbitals. We usually draw them as just these kind of big wings. We already saw they're actually more of like a, what do I call it, a mushroom. They have a tiny little lobe to them, but we don't draw those because this is the part that we're interested in. So our carbons, sorry, I should have made this green, but that's okay, we'll reverse colors. So our carbons have this sp3 hybridized orbital. So there are 4 orbitals in sp3, right? sp3, 4. Carbon is tetrahedral electron geometry. It's also tetrahedral molecular geometry. For each one of these, we have a hydrogen that it is bonded to, and our hydrogen has just the s orbital, which we know is kind of spherical. All right, some of these are more egg-shaped, whatever. And each of our hydrogens are contributing an electron. And so you have the sharing of electrons to form a bond, otherwise known as covalent bonding. Yeah. So we have a molecule. Awesome. Now, this kind of bond is really strong. It's called a sigma bond. One second, I'm just going to check and see. Okay, so it's called a sigma bond, and this is a overlap we call it an overlapping or a head. I'm sorry, an overlapping or a head-on bond. So what do I mean by head-on? It's like if you're in head-on trap, like if you were approaching a vehicle head-on, right? So you're in line with each other and they're overlapping. It's a really strong bond. Sigma bonds are super, super strong. Sigma bonds are formed by the sharing of electrons in our covalent bond. So when we were drawing our Lewis structure, we didn't have the language for it yet, but these single bonds are called sigma bonds, and the Greek symbol for sigma is a little O with a tail on the top, so that is a sigma bond. Very strong, very cool. All right, so of course if there's sp3 hybridization, there's also other forms of hybridization. So one form of hybridization is going to be sp2 hybridization. So if sp3 was 1s and 3 p's, sp2 is 1s and 2 p's. So notice this is for ethylene, which we'll draw in a second, and we have this hybridization of these orbitals to form 3 degenerate, right, equal in energy level sp2 orbitals. These are going to be used for creating those sigma bonds. And then we have 1,2p orbitals. So let's go ahead and start with the Lewis structure, because for all of these, you're going to be starting with the Lewis structure. So ethylene is C2H2. So we have carbon is 4 valence electrons, we have 2 of them. Hydrogen is 1, we have 2 of them. So that is 10 valence electrons. All right, step 1, draw your Lewis structure. Is that right? Yeah. Sorry, it's H4. I was jumping ahead to the next example. Sorry. So that means that we don't have, hold on, let me get rid of this. So C2H4, so this would be 4. So we have 12 valence electrons. So we've used 2, 4, 6, 8, 10. Which means that we have 2 valence electrons left. Notice every one of my hydrogens has one line drawn from it, so I know that they're donezo. Carbon is not happy. They only have 6 valence electrons each. I'm going to use a double bond in order to fulfill everyone's octets, right? So each carbon has 8, each hydrogen has 2. Very exciting. So we have, in this situation, each carbon has 3 things around it. So that would be a trigonal planar molecular geometry. It would also be a trigonal planar electron geometry. So what we see here, if we were to draw our diagram again, right? So we have our carbons. Sorry, my internet is really slow, so I apologize for the lag here. It's making my normally pristine drawings a little less so. All right, so here we go. So then we have our hydrogens. Sorry about that. Okay, so those are our hydrogens bonded to our carbons. We have one more layer to add to this lecture, right? Because it's not layered enough yet. So here we have those same, oh, and I'm sorry, I forgot to draw our carbons that are shared in this bond. So each one of these bonds would be sigma bonds. And they are going to be equal in length from each other. Those are those hybridized orbitals. So our carbons each have our sp2 hybridized orbitals. But let's go back to our PowerPoint. We still have this 2p orbital. So what is it being used for? It's being used to create this double bond. So our double bond, let me get this color, is you can think of this as being perpendicular to the rest of our molecule. Each one of those unhybridized p orbitals is going to be home to a carbon electron, and they are associating with each other in not a head-on pattern like we see with those sigma bonds, but instead parallel to each other. So this bond is further from the carbon nucleus. Further from the nucleus means less stable, so it's going to be weaker, right? Our sigma bond super strong head-on. This other bond, which is called a pi bond, is going to be home to the interaction between carbon's unhybridized p orbitals. Very exciting. Okay, so we have sp3, and then in our 2p orbital, we have the interaction of our electrons forming our pi bond. So every time we draw a double bond, we are actually representing, let's say in black, we're representing that sigma bond, and then that second bond is only able to exist because it is perpendicular to the rest of the molecule. All right, so there's a pretty good picture from our textbook. Right here. So here we have our sp2 orbitals. So you can think of this. This is the native or the hybridized and native orbitals of our carbon. So in the center here would be, this is our carbon, right? Let me redraw that carbon, right? And from that last picture, we know that this would be a bond to carbon, this would be a bond to hydrogen, this would be a bond to hydrogen, all sigma bonds, right? Notice that that is all on the same plane. That's what this gray box is trying to show. Perpendicular to that, we have our p orbital, where we have this loose association between each other. So here we have a sigma bond, you have a sigma bond, sigma bond, sigma bond, sigma bond, and these are pi bonds. So this is a really big thing to understand. You have your trigonal planar electron geometry that's going to need 3 of our sp2 orbitals. 1 p orbital is not hybridized, and that is what allows for a double bond. Double bonds always exist in unhybridized p orbitals. All right, and of course, if there was sp3 and then there was sp2, there's also going to be sp hybridization. So sp hybridization is taking the native 2s orbital of carbon and the 3 2p orbitals, and it's saying, okay, it's going to have linear geometry. It has 2 things around that central atom. I don't know why that's not leaving a mark. Sure. And because of that, we need our 2 sp orbitals, degenerate, same energy level, and now we have 2 p orbitals that are not hybridized. So what does that look like? Well, this is the example that I was trying to jump to. So now we get to do ethylene. So that is going to be C2, H2. Okay, so our carbon, 4 times 2. Our hydrogen, right, this feels familiar, is 1 times 2. So we have 10 valence electrons. Those 10 valence electrons are going to be used to create our sigma single bonds. Oop. Now I'm just combining my examples. Good Lord. All right. All right, my hydrogens are done. My carbons are super unhappy. I have used 6 valence electrons. That means that I have 4 left. Carbon, each one of my carbons wants 4 valence electrons, so I know that these are going to be shared in double bonds. All right, so going back to that cartoon, right? These are my sp orbitals, so in black, we have our sp hybridized orbitals. Then we're gonna have our, oh, let me draw my other carbon first. Then we have our hydrogens. And now we have, wait for it, this is such an ugly color. Let's make them purple. We have 2 unhybridized p orbitals. We're going to draw one of them in purple, right? So these are associating with each other. Come on, there you go. Make the other one in orange. All right, I'm not. Oh, frustration. There we go. These are associating with each other. 1, 2, 3, 4, 5. I don't know why I counted 5. It just felt right. And our, whoopsie, our purple is associating with each other. And you'll notice that where in our last example we just had 1 double bond, now we have 2. So one of them we're representing in p orbitals that are unhybridized, that are orange, and one is unhybridized p orbitals in purple. Very cool. It didn't exactly stay true to our key. So this is unhybridized. That is a UH for unhybridized p orbital. And just imagine that purple is also up there. Okay, so that's sp3, sp2, sp. This can feel a little overwhelming, but ultimately all you're doing is looking at an individual atom in a molecule and saying how many effective electron pairs are there, lone pairs or sigma bonds. We don't count pi bonds here, just in the same way as we did with our molecular geometry. And then you're saying, okay, what kind of orbitals have to hybridize in order to make those sigma bonds? Pi bonds are going to exist in unhybridized p orbitals. You've heard me say that 3 times in this lecture now. All right, so here is another example. So before I had ethylene, now we have carbon dioxide, right? We've seen this before. Carbon, right? It has 2 things around it. These are both double bonds. So if we were to draw, hopefully my program will let me draw this molecule, it would be all right, so I asked myself how many things are around my carbon. There's 2 things around it, 2 oxygens. So it needs 2 orbitals of the same energy level. So that will be 1 s and a p orbital hybridizing to form 2 sp orbitals. Then those double bonds are going to exist in unhybridized p orbitals. Okay, so there's also the opportunity to have D-sp3 or D2-sp3 hybridization. Now, some textbooks will write this sp3d or sp3d and sp3d2. I don't care if you put the D in front of the sp or after the sp. It's kind of a mixed bag depending on what textbook you're looking at. So if you look at YouTube videos or other resources and they put the D at the end, that's not incorrect. It's just, there's kind of two conventions, and I'm sure that scientists in either camp feel really strongly about it. I don't. So do whatever, but make sure it's right? So here in our D-sp3, right, we have those 3 p orbitals, we have our 1 s orbital, and we have our d orbital, right? So we have 5 things, 1, 2, 3, 4, 5, around that central atom. We would think of that in terms of our electron geometry as being trigonal bipyramidal, right? 5 things around that central atom. We need to have 5 degenerate orbitals, so those are going to be D-sp3. D2-sp3 would be an example where you have 6 things around your central atom, right? So you need your 1s, your 3 p's, 2 d orbitals. That would be an example where you have octahedral electron geometry. So this is a really nice slide that just kind of sums up everything that we've talked about here. I really encourage you to go back through your recitation packet and just use the one from chapter 8. You don't need to redraw all of the Lewis structures. Again, chapter 8 and chapter 9 are identical recitation packets. It's just in chapter 9 you're going back through and you're assigning hybridization. So get practice with that. And then one last thing for this is looking at, so this is also, sorry, I forgot I threw this slide in. This is also a really good chart. So number of effective pairs, right? An effective pair being a lone pair or single bond, right? Double bonds, triple bonds count as 1. Now we understand why, because that's 1 sigma bond. The pi bonds, those double and triple bonds, exist in unhybridized orbital. So cool. So those sp, if it's linear, you have sp hybridization, trigonal planar, sp2 hybridization, tetrahedral, sp3, trigonal bipyramidal, d-sp3. So we're just adding another layer of complexity here. Okay, so let's just do a quick example, like something that you'll see in the chapter 8 kind of practice quiz that I'm going to post. So here we have ethanol, and you should notice that our oxygen here is going to be really unhappy, right? It doesn't have a complete octet. I encourage you to go through and actually like count these, and you know what? I am going to really quickly, theoretically really quickly, yeah. I'm just going to kick this over here so we can work through it. Okay, so our oxygen isn't happy, right? It does not have a complete octet, so we need to draw in our lone pairs. And now I can point to any of our atoms that are bonded to more than one other species and say, what is the electron geometry, molecular geometry, and the hybridization, right? So let's look at oxygen because it's the most interesting one. So if we said, what is the let's start with the electron geometry, it would be tetrahedral, which I'm just going to abbreviate because my tablet is not working well, as tetrahedral, tet, cool. So that is the electron geometry. Frustration. Electron geometry is tetrahedral. 2 of those things are lone pairs, so we know that the molecular geometry would be bent, which I will just abbreviate as a B, because again, my tablet hates me right now. And this oxygen has 4 things around it, right? Its electron geometry is tetrahedral, 4 things. I need my S, P, 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 SP3. hybridization. That is the hybridization of that oxygen. Very cool. So there are going to be a few examples of problems like this on the practice quiz for chapter 8 and 9. This is the only additional layer. So it's just a better understanding of those sigma bonds and the pi bonds that we learned about in chapter 8, how they're in relationship to each other, and the kinds of molecular or the kinds of orbitals that they exist in. All right, and that is it for this class, which is crazy. So make sure that you work through that material for chapter 8 and 9, get some practice in, and then you want to start reviewing for your final exam. Crazy. All right.